In the early years of the 20th century, when the automobile was still a mechanical experiment in motion, speed was not yet measured against the effortless performance of modern highways. It was measured against horses, steam locomotives, bicycles, and the limits of human nerve. Roads were rough, tires were fragile, brakes were primitive, and the machines themselves seemed barely separated from the workshops that had created them. Yet within this uncertain world, a new ambition was beginning to dominate the minds of engineers and racing drivers. They wanted to know how fast a motor car could truly go. In 1909, that question led a group of Benz engineers toward one of the most extreme answers ever placed beneath an automobile hood. A 4-cylinder engine displacing 21.5 liters. The number remains astonishing even by modern standards. Today, an ordinary family car may use an engine of 2 liters or less, while some large sport utility vehicles and performance cars operate with engines of 4, 5, or 6 liters. The Benz record engine was larger than several modern engines combined, yet it had only 4 cylinders. Its pistons were enormous, its moving parts were heavy, and the entire engine weighed hundreds of kilograms. It produced around 200 horsepower at a modest engine speed, but the meaning of those figures changes completely when placed in the world of 1909. This was a time before electronic fuel injection, before computerized ignition, before wind tunnels became standard tools of automobile design, before modern tire compounds, before anti-lock brakes, and before engineers could simulate stress, airflow, combustion, and vibration on a computer screen. Every major improvement had to be designed, machined, assembled, tested, and often broken before anyone knew whether the idea would survive. That is what makes the story of the great Benz record car so compelling. It was not simply a machine built to win a race. It was a machine built to cross a frontier. The target that haunted the project was 200 kilometers per hour, a speed that sounded almost impossible for a road vehicle at the beginning of the century. To reach it, the engineers would have to rethink power, stability, strength, and the shape of the car itself. They would also have to accept danger on a scale that is difficult to imagine today. The driver would sit exposed behind a narrow steering wheel with little more than clothing, goggles, and courage between his body and the rushing air. There were no safety cells, no belts, no impact structures, and no carefully engineered runoff areas. A tire failure, a steering problem, or a broken component could become fatal in a fraction of a second. Yet the men behind the project were not reckless dreamers. They were professional engineers and racers, working at the edge of what their technology could achieve. They understood that the car had to be more than powerful. It had to hold together, and so the pursuit of speed became a pursuit of engineering knowledge. Every increase in displacement produced more force, but also more stress. Every attempt to reduce air resistance changed the cooling, balance, or accessibility of the machine. Every test run revealed weaknesses that could not be predicted on paper. The result would become known around the world as the Blitzen Benz, the Lightning Benz, a machine whose name captured not only its speed, but the shock it created in an era when the automobile itself was still young. To understand why the engineers chose such an enormous engine, it is necessary to return to the technological logic of the period. Modern performance engineering offers many ways to extract more power from a smaller engine. Turbochargers compress the incoming air. Electronic control systems adjust fuel and ignition thousands of times per minute. High-strength alloys allow parts to survive tremendous loads at very high rotational speeds. Variable valve timing changes the breathing characteristics of an engine while it is running. Sophisticated lubricants reduce friction. Computer modeling helps designers control heat, vibration, and airflow long before a prototype is built. Early automobile engineers had far fewer tools. Their fuels were less consistent, their metals less advanced, their machining less precise, and their understanding of high-speed aerodynamics was only beginning to develop. If they wanted substantially more power, one of the most direct solutions was simply to increase the amount of air and fuel that the engine could burn. In other words, they increased displacement. Larger cylinders could contain a larger charge. A larger charge could create a larger combustion force. If the crankshaft, connecting rods, pistons, bearings, cooling system, lubrication, and drivetrain could survive, more displacement could mean more power. This approach was already visible in the great racing machines of the period. Engines grew because engineers were seeking performance without the ability to rely on modern high engine speeds or forced induction systems. Benz already possessed a powerful racing platform before the 21.5-Liter record car appeared. The company had developed a 150 horsepower Grand Prix machine, itself an impressive automobile for the period, but the ambition of exceeding 200 kilometers per hour demanded another level of performance. The existing racing engine could not simply be asked to deliver infinitely more by spinning faster. Higher engine speed would have increased stresses dramatically, and materials and lubrication placed strict limits on what could be expected. The safer path, at least in theory, was to build more displacement and obtain the required power at relatively low revolutions. This is one reason the great record engine produced its power at around 1,600 revolutions per minute, a speed that seems slow compared with a modern performance engine, but was entirely logical for its dimensions and era. The challenge was that enlarging an engine creates problems faster than the displacement number alone suggests. A larger piston is not merely a small piston scaled upward. Its mass grows, its surface area changes, its heat load increases, and the forces acting on the connecting rod and crankshaft become more severe. A longer stroke means greater piston speed for a given number of revolutions. A larger bore means greater combustion pressure acting over a larger area. The crankcase must resist stronger forces. Bearings must carry heavier loads. The cooling system must remove more heat. The fuel system must provide a larger and more consistent mixture. The ignition system must reliably light a charge inside a huge combustion chamber. Every gain in power threatens to reveal a new weakness somewhere else. That is why the Blitzen Benz was not simply a crude example of the belief that bigger was better. It represented a carefully engineered response to a specific problem. The engineers knew what speed they wanted. They knew roughly how much power they needed. They knew the existing car could not provide it. Their answer was extreme, but it was not random. It was the product of the mechanical possibilities available to them. And at the center of that effort stood men whose names are less familiar today than the machine they helped create. Among the important figures in the project were designer Louis de Groulart, his assistant Hans Nibel, and racing driver Victor Hémery. Their roles illustrate a truth that is often lost when technological history is reduced to a single inventor. Great machines rarely emerge from one isolated mind. They are created through collaboration between people who calculate, draw, machine, assemble, test, drive, repair, and criticize. De Groulart worked on the design problem from the engineering side. Nibel, who would later become a significant figure in the history of Benz and Daimler-Benz, assisted in the development. Hémery brought something that no drawing board could provide: experience at speed. A racing driver in this period was not merely someone who arrived after the car had been completed. The driver was part of the development process. He could feel changes in steering, balance, vibration, throttle response, braking, and stability long before those sensations could be measured with modern instruments. The communication between driver and engineer therefore mattered enormously. If the car wandered at speed, if the engine hesitated, if vibration suggested that a component was reaching its limit, the driver became the first sensor in the system. The project began with a brutally simple objective. The team wanted a car capable of exceeding 200 kilometers per hour. To a modern audience, that speed may not sound extraordinary because many contemporary performance cars can achieve it. In 1909, however, 200 kilometers per hour represented a frontier. It was faster than most people had ever traveled. It approached a domain associated with the fastest trains and the new world of aviation. The Wright brothers had made their famous powered flight only a few years earlier. Automobile design was changing at a remarkable pace, but a car traveling at more than 200 kilometers per hour would have to manage forces and aerodynamic effects that ordinary road vehicles never encountered. The target also forced the team to confront a basic question of engineering philosophy. Should they design an entirely new multi-cylinder engine, or should they enlarge the proven four-cylinder concept they already understood? The answer was to retain the basic four-cylinder configuration and expand it on a scale that would make the engine legendary. This decision had several advantages. It reduced the number of cylinders, valves, ignition events, and individual moving assemblies compared with a more complex engine. At the same time, it concentrated enormous displacement into each cylinder. That concentration created its own difficulties, but the architecture remained mechanically understandable. The engineers increased the bore dramatically, creating cylinders of approximately 185 millimeters across, while the stroke remained about 200 millimeters. Those dimensions are easier to appreciate when imagined physically. A piston nearly 19 centimeters in diameter is not a small machine component. It is a large metal disc moving repeatedly through a cylinder, accelerating from rest, reaching high speed, stopping, and reversing direction again and again. Multiply that motion by 4 cylinders, connect them through heavy rods to a crankshaft, ignite huge charges of fuel and air above them, and the violence inside the engine becomes easier to imagine. The machine may have turned at only around 1,600 revolutions per minute, but every revolution involved immense reciprocating forces. That is why the engine demanded structural reinforcement. The challenge was not merely to create combustion. The challenge was to keep the engine alive while combustion tried to tear it apart. The final displacement of approximately 21. 5 liters transformed the Benz power unit into something closer in scale to an industrial or aircraft engine than to what modern drivers would consider an automobile engine. Yet displacement alone does not explain its character. The bore and stroke created huge combustion chambers, and those chambers had to be fed, ignited, cooled, and sealed using early 20th century technology. The compression ratio was low by modern standards, roughly in the region of 5, 8 to 1, but again the number must be understood in context. Fuel quality, combustion chamber design, ignition control, and material limits were very different from those of the present day. High compression would have created problems that engineers were not yet equipped to solve reliably. Instead, the engine made power through sheer volume. Each cylinder swallowed a massive charge. Each combustion event produced a heavy push on the piston. Rather than generating power through extreme rotational speed, the engine relied on torque and displacement. To survive, the design required stronger internal support. Historical records describe a move to a crankshaft supported by 5 main bearings, an important change because the crankshaft had to resist bending and twisting under the enormous forces created by the giant pistons. Reinforcement of the cylinders and surrounding structure was equally necessary. The engine itself weighed around 407 kilograms. That figure is revealing. A modern compact car engine can weigh a fraction of that amount. In the Blitzen Benz, hundreds of kilograms of machinery existed simply to create the power required for record speed. The output was approximately 200 horsepower, or around 147 kilowatts, at about 1,600 revolutions per minute. Judged only by modern power per liter standards, the number seems modest. A current production engine of 2 liters can produce equal or greater power, but such a comparison misses the achievement completely. The Benz engineers were working without a century of accumulated combustion science, metallurgy, electronic control, lubrication chemistry, and manufacturing precision. Their engine was not designed to impress a modern dynamometer. It was designed to survive long enough to push a car beyond a speed barrier that had rarely been approached. This distinction is essential because technological history is often misunderstood when old machines are judged only by new standards. The significance of an early engine lies not in whether it would outperform a modern one, but in what it accomplished with the tools available at the time. The 21.5-liter Benz represented one of the clearest expressions of a design philosophy based on large displacement, low rotational speed, heavy construction, and mechanical simplicity. It was a brute force solution, but brute force had to be controlled with precision. The huge pistons had to remain synchronized. The crankshaft had to run true. Bearings had to receive enough lubrication. Heat had to be carried away. Ignition had to arrive at the correct moment. The gearbox and final drive had to transmit the torque without destroying themselves. Even the smallest overlooked weakness could end the attempt. A failed bearing could seize the engine. A cracked component could release debris at speed. A fuel problem could destroy power just when the car needed it most. The engineers therefore faced a paradox. The larger they made the engine, the more power they gained, but the more difficult the machine became to manage. Every increase in scale created additional stress, heat, weight, and vibration. The Blitzen Benz was successful because the team did not stop at enlarging the cylinders. They strengthened the system around them. That is the difference between an oversized experiment and a serious record car. Power, however, was only half of the problem. A car attempting to travel beyond 200 kilometers per hour must fight an invisible force that grows dramatically with speed: aerodynamic drag. At modest speeds, the shape of a vehicle may seem secondary to engine power. At very high speeds, air becomes a wall. The faster the car moves, the more energy is required simply to push the atmosphere aside. Early automobile designers did not possess the sophisticated wind tunnels, computational fluid dynamics, and aerodynamic measurement systems available today, but they were beginning to understand that body shape mattered. The record, Benz could not simply be a Grand Prix car with a larger engine. It needed a body suited to sustained high speed. The resulting form was narrow and purposeful. The occupants were squeezed into a tight space because frontal area had to be minimized. The radiator and front bodywork were shaped to meet the air more cleanly than the broad, upright surfaces common on many ordinary cars. The rear tapered away, reducing the abrupt wake behind the vehicle. Even these early efforts mattered because at more than 200 kilometers per hour, every exposed surface created resistance. The body became an engineering component rather than mere decoration. This was an important change in thinking. Automobile design had long been dominated by mechanical considerations. Engines, gears, chains, axles, brakes, and frames were the obvious subjects of attention. High-speed record attempts forced engineers to treat the atmosphere itself as part of the problem. The car was not operating in empty space. It was moving through dense air that pushed back against every part of the machine. The Blitzen Benz therefore represented a meeting between two strategies. One was ancient in its mechanical logic, used more displacement and more force. The other pointed toward the future, reduced drag through shape. Neither strategy could succeed alone. A streamlined body without enough power would never reach the target. A giant engine inside a badly shaped car would waste too much of its output pushing air. The team had to combine both. Cooling made the problem even more complicated. An engine of 21, 5 liters produced enormous heat, and cooling required airflow through the radiator. Yet opening the front of the car to more air could increase drag. The ideal shape for aerodynamics was not necessarily the ideal shape for cooling. The same tension affected almost every part of the design. Covering components could reduce drag, but might trap heat or make repairs more difficult. Narrowing the body reduced frontal area but left less room for the driver and mechanic. Extending the tail improved airflow but added length. High-speed engineering was therefore a process of compromise. The most dramatic feature remained the engine, but the machine's success came from the way its systems worked together. This is one reason the Blitzen Benz should not be remembered simply as a car with a ridiculous displacement figure. It was an early integrated record machine. Power, structure, gearing, body shape, cooling, and driver control all had to serve one purpose. The target was no longer ordinary racing. The target was the frontier of speed itself. By late summer of 1909, the first version of the great engine was ready for testing. The stage is often overshadowed by the famous record runs that came later, but it was where the project truly became real. Drawings can predict dimensions and forces. Workshop calculations can estimate strength. Experience can suggest what materials are likely to survive. But only testing reveals how an entire machine behaves when every system is working at once. Near the Benz factory, the car began to demonstrate both its promise and its limitations. Engineers watched temperatures, listened for mechanical distress, inspected plugs and bearings, and examined components after runs. The driver reported how the car responded to throttle, how it tracked on the road, and how vibration changed with speed. There was no electronic data logging to produce a clean graph after the test. Much of the evidence had to be read from the machine itself. Discoloration, wear marks, loosened fasteners, oil condition, damaged surfaces, unusual noises, and the driver's memory. Every test was therefore a conversation between human observation and mechanical behavior. One of the early competitive appearances came at the Semmering Hill climb. Here, the enormous Benz faced a type of course that did not necessarily favor its strengths. A giant high-speed engine is most impressive when it has room to accelerate and remain near its ideal operating range. A hill climb demands rapid changes in speed, strong traction, effective gearing, and confidence through bends. The record machine did not dominate automatically. A 150 horsepower Mercedes proved better suited to the event and defeated it. This result was valuable precisely because it showed that maximum engine size did not equal universal superiority. The Benz had been built for a specific mission. Its purpose was not to be the best car everywhere. Its purpose was to travel faster in a straight or gently curving high-speed environment than almost anything else on wheels. The loss at Semmering, therefore, did not invalidate the project. It clarified it. The machine needed space. It needed a surface where the driver could hold the throttle open and allow the huge engine to build speed. It needed a place designed for sustained motion rather than tight competition. That place was Brooklands in England. Opened in 1907, Brooklands was one of the world's first purpose-built motor racing circuits, and its broad-banked sections offered exactly the kind of environment in which engineers could explore high speed more seriously. For the Benz team, Brooklands represented more than another venue. It was a laboratory large enough for the 21.5-Liter engine to reveal what it had been created to do. Victor Hémery would become the man at the center of that test. The question was no longer whether the engine could run. The question was whether the machine could cross the barrier that had inspired the entire project. Before the decisive Brooklands runs, Hémery had already demonstrated the car's potential. In Brussels, he achieved a standing kilometer performance that established a world record showing that the Benz could accelerate with extraordinary force despite its weight and size. But the true objective remained the flying records, where the car entered the measured distance already traveling at high speed. In November 1909 at Brooklands, the project reached the milestone its creators had been pursuing. Hémery drove the Benz to more than 205 kilometers per hour over the flying half mile and more than 202 kilometers per hour over the flying kilometer. The psychological barrier had been broken. The car had exceeded 200 kilometers per hour. For the engineers, those numbers were more than trophies. They were proof that the design philosophy worked. The giant engine could produce the required power. The reinforced structure could survive it. The body could move through the air efficiently enough. The gearing could translate engine speed into road speed. The driver could control the machine. Every major decision made during the project had converged in those measured distances. To imagine the experience, it helps to convert the speed into something physical. At more than 200 kilometers per hour, the car was covering over 55 meters every second. Road irregularities arrived almost instantly. A steering correction that would be gentle at ordinary speed could become dangerous. Wind pressure pressed against the driver's body. Mechanical vibration traveled directly through the frame and controls. The engine, only a short distance ahead, was performing a continuous sequence of enormous combustion events. Each piston was accelerating, stopping and reversing direction thousands of times per minute. The crankshaft was carrying powerful torque pulses. The drivetrain was transmitting that force to the rear wheels. The tires, narrow by modern standards, were being asked to survive speeds far beyond ordinary road use. And the driver sat exposed, with none of the protective systems that define modern motorsport. The achievement, therefore, depended on human courage as much as mechanical reliability. Yet even after crossing 200 kilometers per hour, the project was not finished. Record culture has a natural tendency toward escalation. Once a number becomes possible, it quickly stops feeling impossible. Engineers begin asking how much farther the machine can go. Drivers want a faster run. Promoters want a greater spectacle. Manufacturers want a stronger claim. The Benz had proved that 200 could be exceeded, but its design still seemed capable of more. Europe, however, offered relatively few places where the machine could be unleashed safely at maximum speed. The great record car needed a longer, flatter, more open environment. That search carried this story across the Atlantic, where American motorsport was developing its own appetite for spectacle, daring, and mechanical extremes. The United States transformed the Benz from an extraordinary European engineering project into an international legend. American racing culture in the early 20th century was loud, dangerous, promotional, and intensely competitive. Speed records were not merely technical achievements, they were public events. Newspapers reported them, crowds gathered to witness them. Promoters understood that a machine capable of unheard-of speed could become a sensation. One of those promoters was Ernie Moras, who acquired the first record Benz and brought it to America. There, the machine gained the English name that captured its character perfectly, the Lightning Benz. In German, the idea would become Blitzen Benz, a name that has survived far longer than many of the individual competitions in which the car appeared. The timing was ideal. American drivers were eager to prove themselves, and Daytona Beach in Florida offered a natural high-speed course unlike most conventional tracks. Its long stretches of hard-packed sand provided room for record cars to accelerate and remain at speed. The surface was far from perfectly predictable, but it offered the one thing the Benz needed most: distance. Barney Oldfield, one of the most famous American racing personalities of the era, became one of the men to take the car into this environment. In March 1910, he drove the Benz to more than 201 kilometers per hour over the flying mile. The figure pushed the machine beyond its Brooklands performance and strengthened its reputation. Oldfield's run also revealed the importance of the American record scene. A European machine could arrive in the United States, be placed in the hands of a celebrated driver, and become part of a new culture of speed almost immediately. Yet the story still had not reached its climax. The car would soon be driven faster by another American racer, Bob Burman. In April 1911, at Daytona Beach, Burman accelerated the Blitzen Benz across the hard sand and reached approximately 228.1 kilometers per hour over the flying mile. For a machine created in 1909, the number was extraordinary. At that speed, the car was traveling more than 63 meters every second. In the time required to speak a short sentence, it could cover the length of several football fields. There were no aerodynamic wings, generating sophisticated downforce. No carbon fiber chassis surrounded the driver. No radio linked him to engineers. No digital dashboard displayed tire temperatures or engine parameters. No emergency medical team waited under modern racing protocols. The car depended on mechanical preparation, the driver's senses, the quality of the surface, and a margin of safety that would be considered unacceptable today. Burman's achievement became one of the defining moments in the car's history because it demonstrated how far the original idea could be pushed. The engineers had begun with a target of 200 kilometers per hour. The finished concept was now running nearly 30 kilometers per hour beyond that target. The 21.5-Liter engine had not simply met the requirement, it had created room for further escalation. And the Blitzen Benz had become more than a technical curiosity. It was now a symbol of an age in which speed records captured the public imagination as evidence of industrial progress itself. The fame of the Blitzen Benz was strengthened by the fact that the machine seemed to belong to no ordinary category. It was not a practical road car. It was not a conventional racing car designed for tight circuits. It was not an aircraft, although its engine size invited comparison with aviation machinery. It was a purpose-built instrument for converting fuel, mechanical force, and human courage into speed. That purity of purpose explains why the car still appears so dramatic in photographs. The long hood dominates the body because the engine dominates the design. The narrow cockpit appears almost an afterthought beside the mechanical mass ahead of it. The wheels are tall and thin. The frame is exposed. The driver sits close to the machine rather than isolated from it. Every visible element speaks of a time before high-speed automobiles acquired the smooth, integrated forms that later generations would consider normal. The mechanical components are not hidden because the automobile itself is still visibly mechanical. The driver does not merely operate the machine, he seems to ride within it. That visual character also reflects the engineering priorities of the period. Reliability and serviceability mattered. Components had to be inspected, adjusted, lubricated, tightened, and repaired frequently. A record car that could not be serviced easily would be useless. The machine therefore embodied a balance between streamlining and accessibility. The body was shaped to reduce drag, but the underlying mechanism remained understandable to the mechanics responsible for keeping it alive. Several 200 horsepower Benz record cars were eventually built, and their individual histories diverged as they traveled to different events, owners, and countries. Some were modified, some received altered bodywork, some continued to appear in competitions and demonstrations. The existence of multiple examples shows that the original concept was not viewed as a one-time accident. Benz recognized that the machine had promotional and sporting value. Its speed demonstrated engineering capability in a way that ordinary advertising could never equal. A manufacturer that could build one of the fastest cars in the world could claim technical authority far beyond the narrow market for record machines. The car became a statement about what Benz engineering could accomplish. This link between motorsport and brand reputation would become a permanent feature of the automobile industry. Manufacturers would spend enormous sums on racing, not because racing cars were practical, but because success at the limit influenced how the public viewed the company's road cars. The Blitzen Benz stood near the beginning of that tradition. It proved that engineering spectacle could become commercial mythology. The story extended even to the Bonneville Salt Flats, where another Blitzen Benz participated in record attempts before the First World War. The vast salt surface represented a new kind of environment for speed, flatter and more open than conventional roads or circuits. The idea that the car could travel from European tracks to American beaches and then to salt flats demonstrates how quickly the geography of record breaking was expanding. Wherever there was enough distance, engineers and drivers looked for a way to go faster. The Blitzen Benz followed that search like a mechanical predator built for open ground. Yet the most interesting part of the Blitzen Benz story may be what happened to the philosophy it represented. If a 21.5-liter engine could create extraordinary speed, why did automobile development not continue toward 30, 40, or 50 liters for normal, high-performance cars? The answer lies in the transformation of engineering itself. Large displacement was a practical solution when other methods of increasing power were limited. As technology advanced, engineers learned how to extract more energy from every liter of engine capacity. Better combustion chamber shapes improved the way fuel and air burned. Higher compression ratios increased thermal efficiency. Stronger materials allowed engines to rotate faster without destroying their internal components. Improved bearings and lubrication reduced friction and wear. Carburetors became more sophisticated, then gave way to mechanical and eventually electronic fuel injection. Ignition systems became more precise. Superchargers and turbochargers forced more air into smaller cylinders. Cooling systems improved. Valve trains became lighter and more accurate. Fuels became more consistent and resistant to detonation. The result was a gradual separation between engine size and performance. A smaller engine could produce power that once required enormous displacement. At the same time, the rest of the automobile improved. Gearboxes gained more ratios and became more efficient. Tires developed better rubber compounds and stronger internal structures. Brakes improved from primitive mechanical systems to powerful hydraulic discs with electronic control. Suspensions became more sophisticated. Chassis construction became lighter and stiffer. Aerodynamics advanced from intuitive streamlining to scientific analysis. Every one of these changes reduced the need for a giant engine. If a car could cut aerodynamic drag, it needed less power to achieve a given speed. If it could use a lighter chassis, it needed less energy to accelerate. If the engine could rotate faster safely, it could produce more power from less displacement. If forced induction could increase the mass of air entering the cylinders, the engine no longer needed huge physical volume to create a large combustion charge. By the late 20th and early 21st centuries, electronics added another layer of control. Sensors could monitor oxygen content, temperature, pressure, throttle position, crankshaft speed, and countless other variables. Computers could adjust ignition and fueling in real time. Systems that would have been impossible to manage mechanically in 1909 became routine. The giant naturally aspirated engine was no longer the only straightforward path to speed. In many cases, it became inefficient, heavy, expensive, and unnecessary. But this later evolution should not make the Blitzen Benz seem foolish. Engineering solutions must be judged by the constraints under which they were created. The Benz team did not have access to a century of future discoveries. They used the tools they possessed. Within that world, increasing displacement was rational. The remarkable part is not that the engine was so large. The remarkable part is that the engineers controlled such a large engine well enough to achieve record speed with the materials and knowledge of their time. The machine also teaches a broader lesson about the way technological progress actually occurs. History is often told as a sequence of clean breakthroughs. One inventor creates an idea, another improves it, and eventually modern technology appears. Real development is rarely so orderly. Engineers pursue multiple paths at once. Some prove successful for decades. Others work only under specific conditions. Some seem like dead ends, but teach lessons that later designers reuse in different forms. The Blitzen Benz belonged to a period when automobile engineering had not yet settled on many of the principles that later became standard. Designers were still exploring how many cylinders an engine should have, how large those cylinders should be, where the engine should sit, how the chassis should be constructed, how the body should meet the air, and how power should reach the road. In that environment, extreme experiments were valuable because they revealed boundaries. A 21.5-liter four-cylinder engine showed what could be achieved when displacement became the primary source of power. It also exposed the disadvantages of that approach: weight, vibration, stress, heat, and enormous fuel demand. Later, engineers could move toward different solutions, partly because earlier machines had demonstrated both the strengths and limitations of brute force. The same pattern appears throughout technology. Early aircraft used fragile structures until designers learned how loads behaved. Early computers filled rooms until transistors and integrated circuits changed what was possible. Early steam engines consumed enormous quantities of fuel until improvements in thermodynamics and manufacturing increased efficiency. Progress often begins with oversized, inefficient, mechanically obvious systems and moves towards smaller, lighter, more controlled ones. The Blitzen Benz fits this pattern perfectly. It represents an age when the automobile was powerful because its machinery was physically enormous. Modern cars achieve greater performance with technology that is often invisible: software, sensor networks, precise combustion control, advanced materials, and aerodynamic surfaces shaped through simulation. The old Benz displayed its power openly. The giant hood told observers that something exceptional lived beneath it. The vibration, exhaust, heat, and mechanical noise made the energy visible and audible. This difference helps explain the enduring fascination with early record cars. They make engineering feel tangible. A modern high-performance vehicle can hide extraordinary complexity behind smooth body panels and silent electronic systems. The Blitzen Benz could hide almost nothing. Its engine was too large, its purpose too extreme, and its mechanical character too direct. Watching such a machine would have been a physical experience. The ground would carry vibration. The exhaust would strike the air in heavy pulses. The smell of fuel, hot oil, metal, and dust would surround the car. The driver would climb into a narrow seat, knowing that every important system depended on mechanical parts whose failures could not be corrected by software. The machine demanded attention before it even moved. That presence became part of its legend. There is also a human dimension to the story that can be lost beneath the displacement figures and record speeds. The engineers and drivers involved were working in a culture that viewed technical risk differently from the modern world. Dangerous machines were accepted as part of experimentation. Racing drivers routinely competed on roads bordered by trees, walls, spectators, and buildings. Protective equipment was minimal. Engineers expected components to fail during development because failure was one of the ways they learned. This environment produced remarkable achievements, but it also carried a terrible cost. Many drivers and mechanics of the era were injured or killed. The willingness to accept danger should not be romanticized, yet it cannot be removed from the story. The speed records of the Blitzen Benz were possible because human beings chose to enter a machine whose limits were not fully known and push it toward those limits anyway. Victor Hémery, Barney Oldfield, Bob Burman, and other drivers who handled such cars possessed not only skill but a rare ability to interpret mechanical behavior while traveling at extraordinary speed. They had to feel when a tire was changing, when steering became light, when the engine sounded wrong, when the surface beneath the car was becoming dangerous. There was no electronic warning light to tell them a component was overheating or a system was failing. Their bodies and senses were part of the diagnostic system. Mechanics, too, carried responsibility that would be divided among larger teams today. They prepared the machine, knowing that a loose fastener or overlooked crack could become catastrophic. The line between engineering and survival was immediate. This human pressure gives the technical achievement its emotional weight. The record was not created by numbers alone. It was created by people who had to trust those numbers enough to act on them. Imagine standing beside the car before a run at Daytona. Ahead lies a long strip of beach. The wind carries salt and sand. The engine is already warm, each combustion pulse shaking the chassis. Mechanics make final checks. The driver settles into a position that offers almost no protection. There is no digital countdown, no automated launch system, no traction control. When the throttle opens, the car depends on everything the team has done correctly. The engine begins to pull. Speed builds slowly at first, then rapidly. The surface starts to blur. Wind pressure increases. The steering requires constant attention. The car enters the measured distance at a velocity that would still feel serious on a modern motorway. Yet the machine was designed before many basic automotive standards existed. In that moment, the entire project becomes concentrated into a few seconds. Years of engineering knowledge, months of design and testing, countless workshop hours, and the judgment of the driver are converted into one number recorded by officials. If the number is high enough, history remembers. If something fails, history may remember for a very different reason. That tension was inseparable from the record culture of the period. When viewed from the present, the Blitzen Benz can seem almost unbelievable because modern automotive design has moved so far in the opposite direction. Engineers now celebrate downsizing, efficiency, electrification, software control, and the ability to achieve extraordinary power from compact systems. Electric motors can deliver massive torque without any combustion cylinders at all. Hybrid powertrains combine engines and motors with computer-controlled precision. A road car can produce several hundred horsepower while idling quietly in traffic and meeting emissions. Requirements that early engineers could never have imagined. Against that background, a 21.5-liter four-cylinder engine appears like a relic from another mechanical universe. But that is exactly why its story matters. It reminds us that the path to modern technology was not inevitable. There was a time when engineers did not know which solutions would dominate. They had to test ideas physically, and some of those ideas reached extraordinary scale. The Benz team faced a clear challenge: exceed 200 kilometers per hour. They chose an approach that matched their era. They enlarged a proven four-cylinder design until each cylinder became enormous. They strengthened the crankshaft support. They reinforced the engine. They shaped the body to reduce drag. They tested the machine, learned from environments that did not suit it, and moved to places where its strengths could be used. Hémery crossed the 200 km per hour frontier at Brooklands. Oldfield pushed the speed higher in America. Burman reached approximately 228, 1 km per hour at Daytona. Other examples carried the concept to new events and new surfaces. Step by step, the machine transformed an ambitious engineering target into a historical achievement. The final numbers remain memorable: about 21, 5 liters of displacement, 4 cylinders, an engine weighing roughly 407 kilograms, around 200 horsepower at approximately 1,600 revolutions per minute, and a record speed that exceeded 228 kilometers per hour. Yet the numbers are not the true ending. The real ending is the change in human expectation. Before machines like the Blitzen Benz, 200 kilometers per hour belonged to imagination. Afterward, it belonged to engineering. Once that barrier had been crossed, the question changed permanently. The automobile was no longer a slow mechanical carriage that might someday become faster. It had become a machine with a future that seemed almost unlimited. Engineers would soon pursue 250 kilometers per hour, then 300, then far beyond. Aircraft engines would be adapted to record cars. Streamlining would become more scientific. Supercharging would transform power. Specialized tires, stronger chassis, and new surfaces would push limits outward again and again. The Blitzen Benz did not create all of those later developments, but it stood at an important threshold. It showed what could happen when engineers stopped asking whether an automobile should go faster and began asking only what had to be changed to make it happen. More than a century later, the great four-cylinder Benz still represents that moment. It is a reminder that progress is often driven by questions that sound unreasonable when they are first asked. Why build an engine of 21.5 liters? Why place only 4 cylinders inside it? Why risk building a car for speeds that roads, tires, brakes, and human bodies were barely prepared to handle? The answer is simple and deeply human. Because a barrier existed, and engineers wanted to know what was on the other side. They built the engine because the tools of their time demanded size. They strengthened it because size created violence. They streamlined the car because power alone was not enough. They tested it because theory could not guarantee survival. And they drove it because no engineering achievement becomes real until someone is willing to prove it. The Blitzen Benz was not merely a giant engine on wheels. It was a declaration that the limits of the automobile had not yet been discovered.